Hello, my name is Gatlin now, and I'm introducing Team 22093, or Team as we like to call ourselves. Shown below are the names of our group listed in the order that they're going to be speaking in this presentation. I would like to start this presentation by saying thank you to our sponsor and our mentors. So thank you, NASA, for generating this idea and this challenge. It really helps provide students with a chance to develop possible solutions and ideas to real world problems. And thank you, Dr. Shkuraev and Dr. Thanga, for helping with your feedback, because without you guys, our ideas would not be as developed and as defined as they are now.
As per NASA requests, the Big Idea proposal requires that the robot expands upon or replaces current wheel-based mobility systems. Given that the lunar surface is home to low gravity, craters, invasive regolith, and incredibly rugged terrain, this task was complicated. Our approach to this problem was to find a more biologically inspired design in the image of a dog. With 4 legs, each housing 3 joints, the maneuverability of the terrain exploration and analysis machine, or as we like to call it, team, far outweighs that of your everyday rover. In the interest of budget, the group had to turn away from costly metal components and look to more practical 3D printed components when developing the prototype for this project. The entire body and the 4 legs of team are constructed out of PLA printer filament, as opposed to the desired aluminum body and titanium legs. After a few iterations of the pieces, the prints were successful, and a functional prototype of team was assembled using the 3D printed pieces. While this prototype will by no means make it to the lunar surface, it will be a valuable proof of concept and will allow the group to test the design reliably and cost effectively. Similarly, instruments aboard team were downgraded to meet budget requirements, and while they may not be as fancy as our desired endgame components, they have been tested and proven effective in the development process of team. From this prototype, team has yielded some important results. The fully assembled prototype has proven its ability to better maneuver than a typical wheeled rover, while also showing that it can recognize objects, avoid obstacles, and move to desired points, all important while traversing the lunar surface. Power Systems Feeling Team also demonstrate the capability to provide enough power for key modes, most importantly, walking. Each of these factors are showcasing that team is headed in the right direction when it comes to traversing the challenging lunar surface.
Our conclusions for this project are that we can move the legs of our robot well enough for it to walk properly, and we need to continue testing to make sure that this robot can withstand lunar climate and terrain, such as large inclines and declines, vast temperature changes, and very low friction surfaces. Additionally, we have reached the initial goals of reading the environment to allow the machine to avoid obstacles, and the software systems are able to make the robot walk. Some of our supporting materials for this presentation are our design inspiration and our use of inverse kinematics documentation. The use of documentation for inverse kinematics allowed us to understand how to write the software better to allow our robot's motors to move exactly as they should so that the joints of the legs would not over-rotate.
For this year's NASA Big Idea Challenge, students were asked to design a robot that could handle one specific environment from a list of extreme lunar terrains. We selected steep, rugged terrain near the future Artemis Base Camp. With this selection, the robot had to be able to lift and relocate scientific payloads. The robot had to be designed to be able to lift equipment heavier than itself as well. Finally, the design has to be at least teleoperated. To address these requirements, we created the following mission objectives. The primary mission objective was to create a 3D map of the area surrounding the Artemis Base Camp using a LiDAR system. The robot's secondary objective is to passively collect scientific data about the environment. While completing its primary objective, the robot will be measuring radiation data using a pyranometer and taking pictures of the regolith. After an acceptable model of the environment has been completed, the robot will begin its tertiary objective, which is to relocate equipment for the astronauts.
For this mission, team will be deployed at the Artemis moon base for approximately 9 months. Team is designed to have interchangeable parts to allow for a potential extended mission to go beyond the expected 9 months. Team will launch from Earth in 2026, headed to the Artemis base, located at the south pole of the moon. After approximately 4 days of travel, team will arrive at the Artemis base. From there, it will be unpacked by the astronauts at the base in the next hour. From here, team is ready to begin its tasks and will spend the next 4 to 8 hours moving to a survey site to analyze the lunar regolith and gather LiDAR mapping data, or to assist astronauts around the base with moving objects. After completing the survey at this site, team will relocate to a new site. From here, it will repeat the survey process for another 4 to 8 hours. After approximately 12 hours of surveying, team will return to base to recharge. This process will be repeated for the length of the 9-month mission. This chart shows the logic steps team will take during each activity cycle. Each cycle will last for approximately 12 hours. The first step is to do a diagnostic test to make sure team is in working condition. From here, team will return to base if any issues are found, or if no issues are found, team will receive and move to the location of the first task. Once team has moved to the site for its first task, the environment will be scanned and data will be collected. The data will be gathered with LiDAR and with the black-white camera. If data has already been collected for the chosen area, team will be used to move equipment for the astronauts on the base rather than collect more data. After completion of each task, team will check battery life. If the battery life is sufficient, team will restart this process and begin a new task. If the battery life is not sufficient, however, team will return to the base to recharge.
Moving on to discussion of the prototype. This is an image of the CAD models assembled together in SolidWorks, and this is an image of the actual prototype. The body has 4 main parts that assemble as shown, and the legs are made of 10 unique parts, each that assemble as shown. And although the software for the prototype has not been fully completed, the primary modes for the prototype are known. We intend to have a walking, a turning, and a standing mode. We are hoping to use a Bluetooth controller on design day so that we can move the robot. We are using an Arduino and a PWM board to control 12 individual servos to move the robot. And as mentioned earlier, we are using inverse kinematics in the prototype, and that is used to determine how these servos are going to move to control the robot.
One of the key components for the Team Robot's instrumentation and situational awareness is its LiDAR camera. For the prototype of the Team Robot, a 3D LiDAR scanning camera has been supplemented with a simple LED-based LiDAR ranging camera manufactured by Garmin. While the prototype robot does not map its surroundings, it does have the ability to measure its distance to objects in front of it. The ranging camera is driven by a Raspberry Pi over an I2C interface. One of the primary goals of the Team Robot is to assist astronauts at the Artemis base camp by recognizing, moving, and placing objects heavier than itself. For the prototype Team Robot, emphasis was placed on the object recognition portion of this goal in order to reduce both the complexity and serve budgetary constraints. The object recognition software utilizes an open-source artificial intelligence-based computer vision library for Python called OpenCV. By using the common objects in context, a pre-made data set containing millions of labeled images used for training the OpenCV software, the Team Robot can easily recognize a multitude of different objects from its onboard ArduCam.